All right, so I mentioned last time how we need more tests. And we're going to look at another test right now. This is probably going to be quite a bit shorter than our previous video in some ways, because I just want to kind of go over this one particular test here. And the test that we're going to look at is sometimes called the limit comparison test. Now, the limit comparison test is just like our other tests. It's going to be a test that compares two different series. So or I shouldn't say like our other tests, we have several, but just like the comparison test, this is going to compare two different series. However, it's going to do so in a slightly different way than what we have before. So here's what we're going to be looking at. So let's suppose that we are given a sub n and b sub n, with a sub n bigger than or equal to 0, b sub n strictly bigger than 0. There is a reason why we are doing strictly bigger than 0 that will become obvious in a moment. If the limit as n goes to infinity of a sub n over b sub n, and this is why I said b sub n is strictly bigger than 0, because I want to divide by it. So we're looking at this ratio. Let's suppose that this is equal to some limit L with 0 strictly less than L, strictly less than infinity, exists, then either the sum from n equals 0 to infinity, a sub n, and the sum from n equals 0 to infinity of b sub n both converge or both diverge. So this is a rather interesting result, and it's pretty useful. So why is this going to be true? Let's look at the reason why this limit comparison test works, and then we'll sort of talk about some cases where it's useful. So the proof is going to use the following. So let's let Sn be equal to the partial sums of the a sub i's, and let's let Tn be equal to the partial sums of the b sub i's. So we got to deal with two different sets of partial sums here, sequences of partial sums. So, that is important here. So the first thing to notice is that the Sn and the T sub n are non-decreasing. In other words, Sn plus 1 is greater than or equal to Sn, Tn plus 1 is greater than or equal to Tn. This is actually kind of obvious because we said that the a sub I and the b sub I are bigger than or equal to 0, so each partial sum is either remaining unchanged or it's having something positive added to it. And therefore, we get this nice relationship here. Now, the other thing that we want to look at here. Oh, you know what? I'm actually getting myself confused here. I'm looking at the wrong part of my notes. This is true, but not really relevant for what we're going to be doing here. Actually, what we want to do is... I'm so sorry. I was looking at the wrong spot in my notes. I was like, what in the world is this proof doing? This doesn't make any sense. Okay, so the actual proof that we want to look at is that if the limit as n goes to infinity of a sub n over b sub n is equal to L, then for large enough n, we have two numbers, little m and positive m, with little m less than L less than big M, and little m less than a sub n over b sub n less than big M as well. This just follows from the definition of the limit. But if this is the case, then this means that little m times b sub n is less than a sub n, which is less than capital M times b sub n. Now, if the b sub n sum from n equals 0 to infinity converges, so does the sum from n equals 0 to infinity of little m times b sub n, and the sum from n equals 0 to infinity of capital M times b sub n. And therefore, these a sub n form a bounded sequence, or I'm sorry, the series of partial sums is going to be bounded, and it is increasing, as we argued a moment ago. But when I said, oh, I was starting the wrong proof, well, actually, that is kind of relevant here. And therefore, the a sub n also have to converge. And then we can do the same kind of argument, but sort of flipped around and say, well, if the a sub n converges, then the b sub n has to converge as well. So they both have to work. Or you can simply say that if the sum of the little m times b sub n diverges, then that means the sum of the a sub n's is going to have to diverge as well. In either case, if these converge, then the sum of the a sub n converges. If these diverge, then the sum of the a sub n's diverges. And so we get our result. Now, this is a particularly useful example of where we can make nice this limit comparison is really, really quite useful. And one of the uses of it that I want to show you is how do we do, say, an analysis of the sum from n equals 1 to infinity of 1 over n squared minus 1/2 n. Now, we looked last time at this example, or an example similar to this. The problem was that we couldn't really do this by using the comparison test. We'd like to compare this to 1 over n squared, but it doesn't quite work because the problem is that this denominator is such that the fraction is actually bigger than the 1 over n squared. Let me write down what I mean, because what I just said is probably pretty confusing. This is going to be bigger than or equal to 1 over n squared. So it doesn't quite work. Now, you might be able to mess around with this for a while and get the comparison test to work. Like maybe you could come up with some kind of a factor that makes this work out for you. But there is, in fact, an easier way. And that easier way is to consider the limit as n goes to infinity of 1 over n squared divided by 1 over n squared minus 1/2 n. Well, this is equal to the limit as n approaches infinity of n squared minus 1/2 n divided by n squared. And this is going to be the limit as n approaches infinity of 1 minus 1 over 2n, which is equal to 1. This is a finite number that is neither 0 nor infinite. It's finite and it's not 0. So therefore, this works out. Also, we can say that, yeah, these are all positive numbers here. So we get this, this test does apply. I should have mentioned that at the start. We should really be quite careful to make sure that all of the different things apply. But yeah, they do apply in this case. And therefore, we can say they either both converge or both diverge. But also we can say that the sum from n equals 1 to infinity, 1 over n squared, converges. In fact, this is one of the p series, right? So the sum from n equals 1 to infinity of 1 over n squared minus 1/2 n also converges. And there we go. There's our answer. So here's a little problem for you to spend a minute thinking about here. And I will ask you to pause this and consider it. And the question is whether the following sum converges or diverges. So let's say we have the sum from n equals 1 up to infinity of, let's say, the square root of n divided by n minus 1/2. So take a minute to think about this and see what you were able to do with it. Okay, so how could we deal with this problem? Well, the way that I'm going to do it, there might be other ways of doing it, but I'm going to do a limit comparison to 1 over the square root of n. So we look at the limit as n goes to infinity of square root n divided by n minus 1/2 over 1 over square root n. And this is going to become the limit as n goes to infinity of n over n minus 1/2. And this fairly obviously approaches 1. But the sum from n equals 1 to infinity of 1 over square root n diverges, therefore our sum diverges as well. Now the question is, why did I pick to compare to 1 over square root n? Well, the idea is, I looked at this fraction, and this is square root n divided by something with an n in it. The square root of n divided by n is 1 over the square root of n. And that's where I got this 1 over square root n from, okay? So in general, what you want to do is you want to compare the largest degree thing in the numerator and the largest degree thing in the denominator and see what you get. And that is probably that ratio is probably what you want to do a limit comparison with. Now, there are other tricks for doing limit comparisons as well sometimes that you want to look at, but that is one of the most useful. Here's another example of doing a limit comparison test. So let's suppose that we need to do the sum from n equals 0 up to infinity of 1 over 2 to the n minus n. Well, in this case, I'm going to do a limit comparison to 1 over 2 to the n. Then I'm going to have the limit as n goes to infinity, 1 over 2 to the n minus n divided by 1 over 2 to the n. This is the limit as n approaches infinity of 2 to the n divided by 2 to the n minus n. And this comes out to be 1. You can work out this limit by using L'Hopital's rule if you want to. Think of this as a function and do L'Hopital's rule, and you'll get that this comes out to be 1. Since this converges, our sum converges as well. So we know that the sum from n equals 0 to infinity, 1 over 2 to the n, converges, so our sum does as well. Now, one thing that I do want to mention, in all of these examples that I've shown you, the limit of the ratio has come out to be 1. That's not necessarily always going to happen, but it frequently does. And one of the reasons it frequently does is because if the limit of the ratio comes out to be L, right? So if I have the limit as n goes to infinity of a sub n over b sub n is equal to L, then the limit as n approaches infinity of a sub n over L times b sub n is going to be equal to 1. And the thing is that the sum of the b sub n's converges if and only if the sum of the L times b sub n's converges. So you can always sort of pick your comparison series in a way that this ratio comes out to be 1 if you have a good comparison series to start with. So it's not like I'm saying that you're always going to get 1, but often the way that you make your choice, it's going to work out that you end up with a ratio of 1. At least I tend to choose it in a way that the ratio comes out to be 1. But that's not essential. It's just an artifact of the way that I've been choosing my comparison series. Okay, so I know that this has been a bit of a shorter video, but our last video was kind of extra long and dealt with a lot of different topics. So I'm going to stop here, and I will recommend that in terms of the limit comparison test, as usual, if you want to see some more examples, you should make sure to take a look at Paul's math notes, because he's got all kinds of stuff on there. And, you can go ahead and check his examples, and he has a few more. Again, in terms of what do you pick, you're looking for what you would call the dominant term in the numerator and the denominator. So like in this case, the dominant term is the exponential. In other cases, it might be the highest power of n that you see. But in general, you're looking at these dominant terms, and that's, I said I was done, but I want to actually throw in one more example of these things. So what if you had something like the sum from n equals 0 up to infinity of 1 over n squared plus the cosine of n. Well, this one is going to be a bit trickier. The way that we're going to deal with this one, though, is I'm going to observe that for n bigger than or equal to 1, 1 over n squared plus cosine n is less than or equal to 1 over n squared minus 1. Because the smallest that cosine n can become is going to be a negative 1 here. So this fraction is less than or equal to this fraction. And then what I can do is do a limit comparison to 1 over n squared. And this shows that the sum of 1 over n squared minus 1 converges. And then the comparison test shows that the sum of 1 over n squared plus cosine n must also converge. So in this case, we actually use both tests. Now, what does this limit converge to? I have absolutely no idea. We can figure out what 1 over n squared converges to, but what on earth this thing does, I haven't the foggiest. It doesn't really matter, though. Like I said before, it turns out that for many purposes, we just care whether the series converges. And if it converges, that's good enough for a lot of things in mathematics. And even in terms of practical applications, it's sometimes good enough to get an approximation as well. So there we go. One more example of using the limit comparison test along with the comparison test. Now, you could also, I think, have just done a limit comparison test of this directly with 1 over n squared. Because you would have ended up with the limit as n approaches infinity of n squared divided by n squared plus cosine n. Yeah, this would be fine because this... How would you prove that this works out? Well, you can pretty easily prove that this approaches 1. And one way of doing so is by using the squeeze theorem. This denominator is between n squared plus 1 and n squared minus 1. So yeah, you could have done this with the limit comparison test directly and not worried about the comparison test. I used both of them. This does actually raise one more important point. I'm really going on a long time after I said I was going to be done, but one more important point, that sometimes you can use multiple tests. Sometimes there's different ways of showing the same result. This isn't really that surprising, though. We have many cases in the past where we've seen different ways of getting the same answer mathematically, right? Like when you're solving a quadratic equation, there's often different ways of doing it. Maybe you can factor it by hand, but you could also use the quadratic formula. In other, there's tons of cases where there's different ways of getting to the same result. So there we go. This is one particular result here, and I showed you one way of doing it, but there are others. Okay, so what we're going to be approaching next time is we're going to start looking at some other tests that we can use to see whether or not a given series is going to converge. But I'm going to end things there for the moment, and I will talk to you again soon.